Hey everyone, hope you can hear me. Um, mission. Um, Today, start going over distribution, line protection. As a reminder, no, I'm Leo Gagan with ECI. Um, spend most of my time with protection settings. Um, but This is a recap on the interconnected power grid. To get the big picture. Um, is the way that power flows is it goes from the large generation stations. Voltage really stepped up to go onto the transmission system. From there, it's transmitted long distances because, as we remember, with higher voltage, we've got lower currents, and power losses are I squared times R. And then once the power gets to its destination, it usually goes to a step down transformer. We drop the voltage down. Um, this particular example has a sub-transmission, uh, which, it's not always the case, but this example has it. And then it looks like it steps it even further down to the distribution system. That's kind of what you guys are probably used to seeing as, you drive through neighborhoods. Um, you know, these, these poles over here, that's primarily the distribution system we'll be talking about today. It's usually from 4 to 34 kV. Anything higher than that, I might call sub-transmission or transmission. And then the secondary distribution, which is 120, 240. That little transformer right there is representative of what you guys would probably be used to seeing as just a can at the top of the pole. And then this is actually, bringing it to your house. Your house would use 120, 240, where it's, a single winding that has 240 with a center tap that's grounded. So some of the characteristics of the distribution system, and again, we're focusing on that 34 to 4 range. Like I said, they kind of see in your neighborhoods. That's a typical voltage range. A 4-wire solidly grounded Y system's probably the most common system that you're going to see. With the 4 wires, it does have a ground that goes out with it. Allows for 2 voltages. For example, you'd have 12 kV line to line and 7 kV line to ground. Grounding makes the line safer for the technicians. So if you think if a ground fault were to occur, we're going to have that ground fault current that can be sensed and tripped quickly by the upstream breaker. Yeah, and it allows for the overcurrent protection. I just kind of mentioned the example of that. Another situation, you can have a 3-wire delta systems. They're less common, but they do exist. Haven't seen a lot of these in Maine. They are all over the place in New York. Fairly common in New York. They've got a lot of delta-delta transformers where the distribution system is ungrounded. And they can technically stay in service with a standing ground fault. So what ends up happening on those systems is if a ground fault does occur, that particular phase, let's say it's phase A, will go to 0 volts. And interesting enough, the line-to-line voltages will actually all stay the same. I don't know if I can draw on here. So what will end up happening is we'll call that ground. If you think, okay, phase A, had a ground fault, the voltage is going to go to 0 like ground, but all of your line-to-line characteristics Whoop, my mark is bad. Say B and C. They actually maintain their line-to-line characteristics, and this actually ends up being an overvoltage where those unfaulted phases, rather than see phase to ground current like they normally would expect, they actually see phase-to-phase magnitudes. And it's also tougher to see, but this angle right here, PowerPoint's making it tough for me. That angle right there is going to be 60 degrees. So, a little bit of a phase shift if you were to think in reference to ground. And this actually ends up creating a 3V0, a ground over voltage. So 3V0, because if you were to add up your A, B, and C vectors, they would not come back to 0. Yeah, that's how we could detect that ground fault on that ungrounded system. But we will not have any fault current in that situation. And like I said, interestingly enough, the system can technically operate this way without that ground fault and these line-to-line voltages maintaining their characteristics. It's just the next fault is gonna produce current. So yeah, that's kind of the ungrounded system. Distribution systems have been traditionally radial. That's not the case anymore. Distributed generation is becoming much more common, and I don't know if I call it that anymore. Distributed generation is just expected at this point. Whether or not if I'm doing protection for a distribution system, I just expect it at this point, whether or not they tell me it's there or not. I expect a fair amount of distribution. And when you guys drive down the road, you can see that, right? Every patch of grass that they can't put solar on, they're putting solar on. So, there's a real impact to that. So typical configurations of a distribution feeder. I think we've got an image after this that'll help. So a feeder is one of the circuits out of a substation. At the substation, I've seen it be fed from a breaker, with a relay, but also seen it, commonly where they have a recloser and recloser controller at the station. The main feeder is a three-phase backbone of the service. There may be taps that come off of that backbone. That may be single phase, two-phase, or three-phase. If you have the one-phase loading, you should attempt to evenly distribute that single-phase loading. If you don't, you actually end up with an imbalance that can create a ground fault current. And if you have enough of that ground fault current, you can actually trip off. So evenly spacing out that single-phase loading is important. And then taps generally have their own protection, either fuses or reclosers. So here's a good example of that. I got it from my electrical power distribution engineering book. But mostly to just walk through what we just talked about. As you can see, we got the 12 kV substation bus. This particular feeder is protected by a breaker in this case. Looks like it's got reclosing. It'd be a reclosing relay. Same thing, we'll probably overcurrent relay. As you walk through here, this main line right here is the backbone that we talked about right here. And each one of these branches are the taps. Looks like each one of these taps has a fuse that's protecting it. I don't see any reclosers till you get down here. And then it's it's meant to allow the substation relay to coordinate with that recloser. So that way, if you were to have faults, down in this area, you wouldn't take the whole backbone and the whole circuit. You would just lose this portion. As mentioned, each one of these taps could be single phase, three phase, could be anything. We can see that here, right? Three phase, 4 wire, 2 wire, 1 phase. You got an ungrounded lateral there. I think it's an example that is meant to, encompass a lot of different examples. And then down here, it looks like it's actually got a normally open tie to an adjacent feeder. So you could actually think, in that situation, think of a very similar feeder that, so just imagine I was copying and pasting all of this and putting it, over here. You could actually close that normally open switch. Let's say if this breaker was out of service for maintenance. I don't know why PowerPoint jumped on me like that. But if that breaker was out of service for maintenance, you could actually feed both circuits from one, from one breaker. So radial feeders. The simplest, lowest cost, and most common type of feeder is the radial type feeder. The current magnitude is greatest in the main feeder at the substation and lessens out towards the end of the feeders as currently used on the taps. That makes sense. As current lessens, conductor sizes may be reduced. You may not want to reduce the conductor size if voltage drop is a concern, or if there's a normally open switch that exists to restore the line for permanent outage, it's breaker maintenance. So we talked about that. Note that the previous slide is a radial feeder. So, yep, current flows this way, doesn't flow the other way. I believe we said, at the beginning of this class, radial is a line that only has one positive sequence source. If they were to tie the switch in with the other source over here, it would no longer be radial. But they often don't do that, right? They don't want it to. They often don't want it to be networked. They want it to be radial. And they would only close this guy in if one of the breakers was out of service. And they needed to, to restore the power. But, they often wouldn't make it networked. And we actually might call this a loop scheme, which we'll get into more also. But in this situation, if they were to tie those together, we may not be able to use the same consideration with the conductors going from big to small, because if this small conductor now has to feed all of that load, that may not make sense. And if it was a looped scheme, we may actually may want to give this this recloser directionality, right? So that it can coordinate with faults in this direction. But if it was fed from this guy, or do we just say there's a bunch of stuff going on? It could also coordinate with that breaker for faults going in that direction. So in that loop scheme, directionality may be something we would want. Oh, and look there, loop feeders. A loop type feeder loops through the feeder area and returns back to the bus. See the next slide. We've kind of already gotten a visual for that. It provides two separate paths for load. Usually has a loop tie switch or breaker that may operate as normally open or normally closed. Loop feeders will be used service loads where high service reliability is important. May have one or two feeders or come from two separate buses fed from separate transformers. May have one or two feeder breakers or come from two separate buses fed from two separate transformers if load is high priority. I've actually seen that. I did some work over at Togus, um, the Veterans Hospital there in Augusta a couple years back, and that's what they had. They actually had. It's a fairly big hospital. I think they actually call it a campus, um, but they would have two. We call that the campus that may be miles apart. Um, they had a 34 feed coming in here and a completely separate 34 feed that came from a completely separate substation, different part of the grid coming on the other side, where one was the normal feed and one was the alternate feed. And, the hospital could be fed from either, um, kind of through this, this loop scheme where, um, they had a normally open switch that could be tied. I think theirs actually had an automatic transfer. So if one was lost, it would switch over to the other one automatically. So this one here is not that. It comes from a single breaker, um, but it does allow for maintenance anywhere in this loop. Um, so you can see here, it's got two paths. We got the normally open here, the loop disconnect switch. Um, I've found that most of the time they are normally open, um, but they can be normally closed. Um, in the normally open situation, we're going to feed current, all the way, to that tap. Um, we'll feed current all the way to that tap, but that's normally open. If you close it, you could feed both. What ends up happening is if this is normally closed, fault detection might get just a little bit more challenging. Um, well, with a single feeder, I guess it wouldn't, but double feeder it would. Because let's say you had a fault right here. It's going to be easy for current to flow to get there, but much harder for it to come back around. Single feeder wouldn't be an issue, or single breaker wouldn't be an issue because, we would trip off. But if we had two of these, let's just pretend that middle part didn't exist. It'd be more difficult for current to flow all the way around to detect that. We'd have to, rely on a sequential trip. So typical distribution system equipment. Switches, fairly simple. A device for making, breaking, or changing the connection in electric current. You've got your load break switches. You've got switches that can't break load. They can almost, or let's just say they can never break fault current. So keep that in mind. A fuse, another pretty simple device. It's an overcurrent protection device with a circuit opening fusible member directly heated and destroyed on the passage of overcurrent in the event of an overload or short circuit condition. It's basically really small wire, a fuse. As current flows through and it gets hot, it melts, and it melts to isolate the or remove the current flow. A little more to it as we'll see with different types of fuses, but it's the general idea. Recloser, an overcurrent protection device that trips and recloses a preset number of times to clear transient faults or to isolate permanent faults. So we're getting a little bit more up here into complexity. A recloser, as we mentioned before, It's kind of similar to a breaker, where it can, interrupt fault current. You probably don't notice them, but if you work with them, you tend to notice them up on poles pretty often. They're often controlled by a recloser controller, which we'll get more into, which is very similar to a relay. But the main difference is, they're usually in a cabinet at the pole. They usually have an umbilical cord, that connects to the recloser controller. And the recloser, oftentimes they're powered from the distribution system itself, with a little bit of a battery backup. But and then after that, we got the line sectionalizer. A sectionalizer is a protective device that automatically isolates faulted sections of the line from a distribution system. So similar to a recloser, but it actually doesn't interrupt it. It waits for the high currents to go away, then opens. So different levels of, I guess, complexity here. Some things I probably could have added since then. Trip savers are starting to become fairly popular. If you can think almost a combination of a fuse and a recloser, something that's meant to have the physical footprint of a fuse, but kind of the ability to interrupt for like a recloser. They're getting pretty popular. So switches. A disconnect switch, a switch designed to disconnect power devices at no load conditions. It's not rated to break load. So in that situation, the circuit would need to be dead completely before we open up that switch. No voltage on either side. A load break switch, which is a switch designed to interrupt load currents but not fault currents. So in that situation, you can open up, a circuit or line, even if there's load flow. You don't have to de-energize the line first. You can keep it energized and, open that switch on the line. The last is a circuit breaker. I guess a circuit breaker is technically a switch. And it has the ability to interrupt fault currents. Be used as a protective device. Fuses. Fuses designed to blow within a specified time for a given fault value. A fuse has in its timing characteristics, two components: a minimum melt curve, a plot of the minimum time versus current required to melt the fuse. The fuse may be damaged permanently if this curve is exceeded. And then it's got the total clear curve, which means once we get to that part of the curve, that fuse has blown. The biggest downside to a fuse is they need to be replaced, right? Once a fuse is blown, we don't have any technology to tell us, where it was blown, when, how. You have to send a technician out to find it. And then once he finds it, he needs to replace it. And the old one, goes in the trash. Definitely the biggest disadvantage. There's no, or the restoration time on it is, very long compared to a lot of our other options. Kind of that sequence we just talked about with a technician going out. That may take a couple hours. As compared to, let's say a recloser. A recloser knows that most faults are temporary, and it actually automatically recloses and is successful most of the time. Maybe it was a squirrel that got in between an energized conductor and a grounded piece of equipment. Once that squirrel catches on fire and falls to the ground, we're good to reclose. Sorry if you feel like squirrels, but with a fuse that doesn't matter, right? We're still sending someone out there to replace the fuse, and you're going to be out of power for a couple hours. So, biggest disadvantage. And the other challenge with fuses compared to some other options is fuses operate on phase current, right? We have one on phase A, phase B, phase C. They operate once we get up above, up above phase current. We don't want them to operate on, normal load, because then you're going to lose power. So they need to be set up above loading. And a lot of the times it's not practical to coordinate these fuses with other ground elements in the area which operate off of the imbalance, because those guys are set more sensitive than load. Sometimes it's challenging to coordinate fuses with with the the ground overcurrent elements in the area. So one type of fuse is an expulsion fuse. Probably one of the more common, I guess you'll see. So the fuse link acts as a weak link that can melt due to heat associated with the overload, fault current. On that, fuse links use various materials and dimensions that determine the time current characteristic. And then the fuse is contained in a tube with a deionized lining. When the fuse link melts, an arc is created that decomposes the lining and emits deionizing gases that help extinguish the arc. Right, because as you separate energized equipment, there generally is an arc that needs to be extinguished. And then current is fully interrupted at a natural zero crossing. And then with this, high pressure gases are then expelled from the ends of the tube. A good visual here. We can see an expulsion fuse operation. Kind of looks like an explosion, but it's not. This here is, an example of the high pressure gases that are expelled from the end of the tube. We can see that here. So we talked about them using various materials and dimensions that determine the time current curve characteristic. Here's an example of this. It's from Aspen. Looks like it's a 34 kV SMD 1A slow speed 200 amp fuse from S&C. If you go to their website, you can get all of this information. It has a time current curve number. Usually what I would do is, let's say, I saw a transformer nameplate and it'll specify a fuse part number. I'll go to their website and they'll give us this time current curve number right here. So then from there, when I'm trying to coordinate with that fuse, I'll go into Aspen and I'll try and find that time current curve number, which we can here. So before we talked about the total clear time and minimum melt time. The top region here is the total clear time, and the bottom portion of the region is the minimum melt. Anywhere in between is kind of a situation where you may permanently damage that fuse, but it may not blow and interrupt the fault current. I guess keep that in mind. When you do coordinate with these fuses in Aspen, if you were to put in, an upstream or downstream relay or recloser or additional fuse, You can actually choose if you wanted to, um, give you the time differences between the minimum melt and the total clear. A lot of the times, if you had an upstream device that you want to operate slower than the fuse, you do see difference on that total clear time. Um, you know, and then if you were going to have a downstream device, um, from that fuse, you would want to coordinate with the minimum melt, right? Because you want the downstream to device to be able to operate before any damage to that fuse occurs. So, here's an example of that same fuse and what we might get from the the manufacturer website. Um, it's the same fuse, the 34 kV SMD fuse with the same time current curve number. Uh, it looks like in this situation, they give a PDF up on the right of what the characteristics are going to look like. And those are different sizes, whether it be, 200 amp, 100 amp. Looks like the small size of 15 amp. But it also looks like um, they have an option to recreate this in Excel, um, which I think we'll be doing in a homework assignment where I've done that. I've created a handful of fuses in an Excel spreadsheet. And I've actually also created the relaying characteristics in that spreadsheet, so we can do some coordination with that. Aspen is very user friendly for doing that, and um, and as a professional working for a for-profit company, we use Aspen, but the licenses are pretty expensive, um, and not readily accessible. Say a nonprofit organization like Humane. Um, so unfortunately, you guys probably won't have access to Aspen. Um, but I threw together some Excel spreadsheets that should help us get the general idea. A current limiting fuse, a little bit different than an expulsion fuse. Um, they're actually able to limit the available fault current through the fuse fairly quickly. Or not instantaneously, but fairly quickly. For a current limiting fuse, the tube is filled with sand, and the arc causes the sand to melt into glass. Um, this glass restricts the arc by increasing the resistance and reduces the current to zero. Um, it's very fast, a lot quicker than the expulsion fuse, where we talked about it needing to get to a natural zero crossing before it isolates the fault. Um, for this current limiting fuse, it can do that before the first zero crossing, so a lot quicker. In addition to a time current curve, current limiting fuses have a let-through curve. So here's an example of one of those let-through curves. This curve has 3 fuse characteristic lines. This is just a simple 25K fuse, 25 amp fuse shown as an example. The single diagonal line represents the RMS current to the peak current. So you can see on the bottom, we have an RMS value. On the left, we have the peak value. And those really just relate, as RMS does to peak, 2 times the square root of 2. So for this particular example, the curve has about 6,000 amps of symmetrical fault current available. We'll say that, that's before the current limiting fuse. You'd get that from a fault study. And we can see here that this top line is being used for our 25K fuse, or a 20 if we had a 20. And then we also have some lines for 15 and 12 and some lower values like 10, 8, and 6. But for our 25K, if we were to think, okay, at the location of the current limiting fuse, there's 6,000 RMS amps available as a worst case scenario. For this 25K fuse, the process is to draw a horizontal line once you get to the intersection over to your diagonal. And then if you wanted to know how much current the fuse is going to let through, you can either draw that line back down and it'll give you, the let through current as an RMS value, or you can draw it to the left and see what that peak value is going to be. And when I say peak, 2 times square root of 2, or I guess if you were to think, of a DC offset with a sine, riding on top of that, it's kind of what that represents. So yeah, I think I went through that process probably a little quickly. Some more detailed instructions there off on the left. Coordinating with fuses. We can see here we've got a pretty inverse shape. By inverse, I mean it's very vertical, as opposed to a horizontal type shape. We would want to have a similar characteristic when we want to coordinate it with it. A good rule of thumb that I usually use is a U4 from SEL is a good curve. It tends to fit that shape, fairly well. Coordinating time intervals, requirements may be specific to utility. A typical interval is 120 milliseconds, or a relay operate time that's 130% of the fuse total clear time for the maximum fault current. That, I believe, comes from the IEEE. But I've seen all sorts of different requirements from this from different utilities. Some places just have a hard-coded 200 milliseconds. Some places have 300. Generally, your CTIs, when coordinating with fuses, can be a lot smaller than if you were doing coordination with, like relay-to-relay coordination. And the primary reason for that is just because this is the total clear time, right? Once we get to that total clear, the fault has isolated. If you were doing relay-to-relay coordination, you need to consider a handful of other things. Like on a relay, the curve shows you the relay, operate time or decision-making time. But it may not include, maybe the one cycle for the, for the breaker, or the one cycle for the relay contact to close. Let's say you've got a 3 or 5 cycle breaker. It doesn't include that breaker operate time. So that time, has to be a little bit higher, but it can be a little bit lower with fuses as well. And then honestly, you can go, if you have reclosing, it may even be acceptable to go even closer than that. If we think back to way back on here for coordination with a fuse, here we go. If we were to think of the coordination between, let's say, this breaker and that fuse, even if we didn't have a full coordinating time interval, a a lot of the times you can think, okay, the fault happened. Both the breaker and the fuse saw it. We may not have had a full coordinating time interval, but maybe the fuse blew and the breaker tripped, but the breaker reclosed. Well, maybe that, depending on your utility, maybe they're okay with that. Maybe they're not, but maybe they're okay with that. That would be a way for the customers to, um, for the customers to have their power restored. And you can even almost take that a step further and say, okay, maybe the fuse didn't blow, um, but the breaker tripped, and we damaged that fuse to the point that it no longer has that same characteristic. It has a more sensitive characteristic because it's been damaged and weakened. And then the breaker recloses, the fault's still there, and maybe then the fuse does interrupt it first. And again, maybe acceptable with the utility you're working with, it may not, but it's a consideration. And then, as we talked about, ground relaying is often set more sensitively than fuses. Um, a fuse must be set above the load, we talked about, where a 51G may be set less sensitive than load because it's really just looking at imbalance. It could be as little as, depending on your system, maybe 30% of peak load. Um, on a transmission system, you tend to have less imbalance, but on the distribution, it may be a little bit higher. Sometimes we'll actually pick an acceptable intersection point between the fuse and the relay to give the fuse ample time to blow. So if we think of let's just think of this 200E1 all the way to the right here. Okay, well, let's just think of the one all the way to the right there. Um, and I know it's tough to see. I tried to zoom in, but I didn't like it. Yeah, it's not going to like it. But let's say we had an intersection point in this range where the that looks like the intersection will go up around maybe 70 seconds. I mean, we gave that fuse 70 seconds. That was plenty of time, um, to operate. We would still have this characteristic over here for for high impedance ground faults that maybe the fuse can't detect. But that intersection point is, depending on, you know, what utility you're working for, um, maybe something they're willing to accept. And again, you have that intersection, right? Because the ground element is more sensitive than the fuse. If it's more sensitive at one point or another, you're gonna have an intersection. It can't be avoided. Uh, okay, so derating fuses for coordination. The load side fuses, so we'll call them downstream fuses. And we touched on this briefly just a few minutes ago. So let's say even though the first reclose or fast curve operates before the fuse minimum melt time on the fast curve, the fuse will experience heating. So we talked about that. It may be damaged. During the next fault, the fuse will already be warm and must be derated to prevent false operation on the second fast curve. Um, the longer the open interval, the more time the fuse has to cool. And the relay recloser fast curve maybe shifted up by a K factor represent this D rating. Okay, so I'm guessing we have, oh, we don't have an example of this here. Okay, probably not a great example. We didn't get into fast curves, which we will here in a few slides. Um, so this we're saying we've got the load side fuse, and we're using fast curves. So this is actually an example where we're trying to save the curve. If you think of the curve being the fuse curve being right here, and we can make that a little bit thicker, right? Because we got the minimum melt and total clear. We've got something called a fast curve on a recloser. That's intended to save the curve, save the fuse. We'll say that's here. So a fault happens, let's say with this magnitude. Um, the recloser is successful in taking it first, but that fuse is still warm. We may not have even gotten to the minimum melt, right? We haven't gotten to the minimum melt. We haven't damaged it, but it's still warm. Um, so depending on how long this open interval is, um, how long it is before it closes back in, that really determines how long um, it has to cool back down. So let's say we had an open interval of 30 cycles. When they say we're going to give the recloser a K factor to be shifted up, we would essentially take this time and multiply it times 1.25. So it would just push it up a little bit into that fuse, and make the coordination just a little bit tighter. Um, you could also do the same thing, right? If you wanted to, instead of multiply times 1.25 to push the relay current up, you could divide by 1.25 and push the fuse down. Right? The ultimate goal is to make that coordination uh, um, essentially tighter. Um, and then this applies for one or two fast curves. Um, let's say it trips, recloses, trips again, recloses again. That'd be the two fast curves. And it experiences that heating twice, so that factor is just a little bit bigger. Um, so a good example. I don't think I've had to do this for any type of coordination before, but again, it's a real consideration. And I actually also tend to spend more time on the transmission system, but um, I could see where we would definitely want to consider that in a fuse saving scheme. So the next type of equipment, more complicated than the fuse, is a recloser. Um, Reclosers have fault interruption capabilities similar to breakers, but they're smaller than breakers. Um, Reclosers are generally pole mounted. We can see in the picture there. It's from a Viper ST catalog. Um, I guess seeing this image here, I guess now if you're driving around town, and you look up on the poles, you're going to start to see a lot more of these. You notice them once you know what they look like. So reclosers often have what's called a recloser controller, um, which is very similar to a protection relay as far as operation and usability and things like that. Um, and then these are designed to automatically reclose after a fault has been interrupted. But it's all based on the recloser controller and how you want to program it and set it up. Some things to look at with this particular recloser. It looks like this particular recloser has got two voltage transformers, one right there, one right there. Um, they may be used to um, drop the voltage down in order to sense voltage on line side or load side. Um, reclosers tend to use something called a low energy analog um, signal. Um, or they could be used to actually power the recloser controller. Right, drop it down to 120 and power the recloser controller. Um, you can see here, these are actually called yellow handles. We've got one per phase. In an emergency situation, a technician can actually take an insulated rod and pull on one of those to trip it. Um, I would probably personally just hit the trip button on the recloser controller, but that's pretty standard for most reclosers. And we can see here current comes into one side, kind of through here, goes up through and out that way. And the interrupting device is right in here. Let's see, can we see the CTs come off of these? And it's tough to see. Okay. So some recloser ratings. Almost all the same ratings that you would see on a breaker nameplate. The continuous current and interrupting currents are generally less than breakers, right? Makes sense. They're quite a bit smaller, quite a bit cheaper. But some typical ratings on here. You might have a 38 kV a recloser. That'd be good on maybe a 34 system. Maybe that 38 kV recloser can handle 800 amps continuously, but the most that it can interrupt under a short circuit situation is 12 kV. And that's symmetrical right there. So when I say it can interrupt 12,000 amps, that's of a symmetrical current. It's saying it can break 32 kV of asymmetrical peak current. So that would be the your AC riding on that DC offset in the peak there. And then you've got your duty cycles that it can handle, which is how quickly can it reclose and charge back up and things like that. And then how many operations it can have. All very similar ratings that you would see compared to a breaker. So this here is an example of a recloser controller. You can see it comes in a prefabricated cabinet, and you can see pretty good place right there to hang it right on the pole, right? But it's got some convenience definitely built in. You can see it's also got some other functions, right? It's got a receptacle if you want to plug your laptop in. It's got a battery right here. If voltage is lost from the the VT here, it can keep itself powered for a period of time. Of other breakers in here, to isolate things. But the recloser controller itself is this blue box, very similar to a lot of our other blue boxes, kind of like we've seen in the lab, right? The SCL 451s, 421s. Very, very similar as far as operation. They work. These particular ones, the 651Rs, you program with accelerator, just like a 451 or 421. But there are definitely other types of reclosers out there. I believe Beckwith has one. Siemens. There's a handful. But like I said, we tend to use the SCL ones because they're pretty user friendly, and you guys have them in the lab, so good example. Yeah. So some recloser curves. We've been talking a lot so far about some of the more typical relaying curves, which by relaying curves I mean U3, U4, U2, very very common. 651Rs can actually replicate some of the older electronic recloser curves, which we can see here. They've got old designations and new designations, but they're the same curve essentially. Yeah, these curves, typically used for the recloser controller applications, as opposed to like I said, the U3s that are breaker relay. And then the ones that I have highlighted here, 117, 105, 113, and 131 are super common for Central Maine. It kind of goes back, I'm sure, many years where, now we're replicating them in the 651Rs, but they had them in the 351Rs. They had them in their electronic reclosers. They've been just trying to keep that same characteristic for a long time. So the ones we talked about there, get out because they're good examples. The 105, 117, 113, and 131. So here they are here, for example. Have a fast phase curve, a slow phase curve, a fast ground curve, and a slow ground curve. Well, my slides may be a little bit out of order, but what we were talking about here with the fuse saving, we mentioned a fast curve on this slide. I guess probably did this slide a little bit early. It's great to see it here. So these are our fast and our slow curves. Red being the phase and blue being the ground. So what I was talking about with fuse saving is let's say that fuse had a characteristic that brought us right down through here. Well, we know that most faults are temporary, right? Let's go back to that squirrel situation. Squirrel bites into it. He burns up, he falls to the ground, and we should be able to restore things after that. Well, in that situation, let's say that our fast curve operates, and the fast curve, which the phase fast curve, this red one right here, let's say that it operates so fast that our fuse isn't damaged at all. The downside to that is we have tripped the whole circuit where just that one lateral or just that one tap could have isolated it. But the benefit to that is actually that we saved that fuse. We were able to trip it and reclose it successfully. And we didn't have to send a technician out to replace that fuse that had blown. That's great. No one lost power for an extended period of time. It costs a lot of money for the utilities to send out these technicians to first off find it, right? Find the blown fuse, but then replace it. So there's a reduction in operating costs. Like I said, the only real downside is the whole circuit lost power for maybe 5 seconds, or whatever that first opening interval is. I'm sure you've had that at your house, right? You lose power for 5 seconds, comes back on. It stinks because you gotta reset the microwave, but or the clock on the microwave. But you're not that mad about it. So I mentioned before about the recloser umbilical cord. Um, that is what goes between our recloser and our recloser controller. It tells us a lot of things, right? It tells us if the recloser is open, if the recloser is closed. Um, the recloser has those VTs on there, and it also has CTs on there, so it sends voltages and currents over. Oftentimes it'll tell us the status of that yellow handle. But this is how all the information is sent from the recloser to recloser controller. That's how the recloser controller tells it to trip and close, is over that umbilical cord. So you can see it here. As we talked about, we've got a potential transformer, brings it down to 120 volts. It goes onto that umbilical cord, comes down and goes to our recloser controller. Then we have our 42-pin control cable that takes all of that information brings it to our controller also. And then we have our trip signals that go back. So as mentioned, it brings voltage for power, trips commands, close commands, and then it sends information such as digital status, CT currents, and PT voltages. All the same information we generally want, a breaker and a relay, right? So here's more of a schematic diagram of that information being given. If we look, this dotted line represents the recloser. That dotted line over there represents the recloser controller. And you can see the connection points on that 42-pin, umbilical cord. So on the left, we've got our AC connections. We can see up here, we actually have what's called that low energy analog voltage. So it's not your traditional VT. It's actually a voltage divider with capacitors that brings a voltage into our relay. We see here we've got a source side and a load side. Source side being your utility, load side being the rest of your load. Current flows from the utility to the load. But we can see here we've got one set of voltages on the source side. We've got another set of voltages on the load side also, it looks like, which is convenient. We haven't gotten into it a lot, but you can use that for things like sync check, reclosing supervisions like live line, dead bus, deadline, live bus, all of those things. And then we've got our CTs right here. It's bringing our current into our relay. And then this breaker right here is meant to be representative of that interrupting point on the recloser. So that's all of your your AC connections in this particular example. There are tons of others, but this is a pretty good one. So then same thing over here. This is our recloser. It's our recloser controller. And these appear to be our trip commands. So you've got your trip coils right here. And then these, they actually look like they're represented as, and they're not, but it looks like they're representative almost as transistors to show when the settings are asserted or deasserted, and how they how they drive the trip coils. Um, so yeah. Um, so a line sectionalizer, similar to a recloser. It's just it doesn't do that that isolate. It doesn't actually do the isolation itself. It waits. Uh, so a line sectionalizer is a protective device that automatically isolates fault sections from a line from a distribution system. So the sectionalizer counts the operations of the upstream recloser. So the sectionalizer is typically set to open at one less operation than the recloser will lock out for. So the sectionalizer does not have any fault interrupting capabilities of its own. It must wait until the upstream recloser or breaker is open before opening itself. So what does it mean by this? It opens at one less operation than the recloser will lock out for. Um, so let's go way back. I can erase all of this. I don't think I can. Um, but let's say we had, say we've got a breaker, uh, got a sectionalizer, then that goes on to a bunch more of load. So basically, the way the sectionalizer is going to work is let's say that this particular breaker has 4 reclose attempts. It's got 4 reclose attempts. So let's say a fault happens down here. Our sectionalizer does not have interrupting capability. So as the fault happens, let's say we've got the 4 reclose attempts. What's going to happen is we're going to trip, reclose, trip, reclose, trip, reclose, trip, reclose, right? We've got 4 attempts, and then it locks out. So this guy right here is going to be set 1 less than that. So let's say we trip, reclose, and then we trip, and sorry, we trip, this guy trips. And on that third trip, we're going to have an open interval. Let's say it's a 10-second open interval. In those 10 seconds, this guy is going to know, okay, I don't have any voltage here. I don't have any voltage here. I was able to sense a loss of voltage 3 times, 1 less than the recloser. I'm going to open. And then when this guy opens, it isolates that fault. On the very last reclose attempt, this breaker up here is able to successfully reclose and, let's say prevent, all of these tapped loads from losing power. So that's kind of the idea of the sectionalizer there. But yeah, so I think we're at a pretty good breaking point. Um, Kind of the way that I anticipate doing this particular section on distribution protection is we'll have this, this lecture here that we just did. We'll have another lecture on Thursday where we finish out the slides. And then the following Tuesday, we'll have a recording down in the lab. I've got the 451 there programmed to do a handful of things that you would typically see, in a distribution circuit. Like it's got some overcurrents, it's got some reclosing schemes, and it's got a handful of other just good logic that's cool to run through. So we'll take that day and we'll spend it in the lab. Um, so, yeah, thank you for your time, and I'll see you on Thursday.